Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here's information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today for exam LTAM, long-term actuarial models. It's problem number 3 from written answer section of the last spring 2019 course LTAM examination. Diana is a member of a pension plan that offers an annual retirement pension of 2% of the member's career average earnings for each year of service. At the valuation date, Diana is exactly 63 years old, has 30 years of service, and her total past earnings are $2,500,000. Her salary in the year following the valuation date will be $160,000 if she works for the full year and is paid in level monthly payments. You are given that the pension is paid as a monthly life annuity due. Members can retire at any time after age 60 without actuarial reduction of benefits. There are no benefits other than the age retirement pension. The traditional unit credit approach is used for valuation and funding. The valuation uses the standard service table, which is part of the standard ultimate life table given to you on the test. And you can find that table at smarturl.it/SULT. All lives retiring before age 65 are assumed to exit exactly halfway through the year of age. Mortality after retirement follows the standard ultimate life table with uniform distribution of deaths. The uniform distribution of deaths assumption applies to the time during the year of death. Interest rate is 5%. That's the same rate that is used in standard ultimate life table. A double dot 63.5 upper 12 is 13.514. A double dot 64.5 upper 12 is 13.231. A double dot 65 upper 12 is 13.085. Part A. 2 points. Show that the actuarial liability for Diana is $595,000 to the nearest 1,000. You should calculate the value to the nearest 1. B. 3 points. Show that the normal contribution for Diana is $36,000 to the nearest 1,000. You should calculate the value to the nearest 10. C. 3 points. Diana is eligible for post-retirement health benefits. The benefits are provided through a group insurance policy with premiums paid annually starting immediately on retirement. You are given the following information. Annual premiums are based on the retiree's age last birthday. The first premium is paid immediately on retirement. The premium for a new retiree age 60 last birthday is $2,000 at the valuation date t = 0. For a new retiree age Y last birthday retiring t years following the valuation date, the initial annual premium is B of YT equal to 2,000 times 1.035 to the power Y minus 60 times 1.03 to the t for Y equal to 60, 61 through 65 and t greater than or equal to 0. A double dot B 63.50 is 30.42. A double dot B 64.50 is 29.124. A double dot B 65.0 is 28.487. Calculate the expected present value of Diana's supplementary health insurance benefit. And here's a solution. Part A. The actuarial liability for Diana is calculated using the data in the standard ultimate life table and standard service table. So the accrued liability at time zero, we can write it as reserve, and that's actually a notation in the book. That is the main textbook, is 2,500,000 total pensionable earnings times 0.02 benefit accrual rate times R63 over L63, so the number of people retiring at age 63 divided by the population at time 63, so the probability of retiring at that age. Because the benefit is paid in the middle of the year, this is multiplied by 1.05 to the negative 0.5 times the annuity in the middle of the year, annuity factor in the middle of the year. So this is a benefit rate times probability times discount factor times the cost of annuity, basically. So A double dot 63.5 upper 12, plus the same for age 64. Again, the benefit here is paid at age 64.5. That's why the annuity factor is at age 64.5. So this is R64 divided by L63 times 1.05 to negative 1.5, because there's 1.5 years between age 63 and 64.5, and then the same for age 65, 2 years after age 63. So R65 over L63 times 1.05 to the negative 2 times A double dot 65 upper 12. Okay, 0.02 times 2,500,000, that's 50,000, over L63, the common factor in all of those expressions. Well, 1 over L63 is the common factor, and then it's R63 over 1.05 to the power 0.5 times A double dot upper 12 63.5 plus R64 over 1.05 to the 1.5 times A double dot 64.5 upper 12 plus R65 over 1.05 squared times A double dot 65 upper 12. And all of those numbers are in the standard service table and standard automatic life table. We plug them in and we get approximately, after calculation, 595,132.40. This is 595,000 to the nearest 1,000. For part B, recall the standard recursive formula used for calculation of normal cost and normal contribution. Accrued liability at time zero plus normal cost is the expected present value of benefits for mid-year exits plus 1.05 to the negative 1 times the probability of remaining in the zero state times accrued liability at time 1. So the expected present value of benefits for mid-year exits, that's 2.5 million plus half a year pensionable earnings times 0.02, the accrual rate times the probability times the discount factor times the cost of annuity at age 63.5. All of those things can be looked up in the table. We plug them in and we get 64,579.98. Also, the present value at the beginning of the year of the accrued liability at the end of the year, actuarial present value is calculated by taking the present value discount factor times the probability of remaining in state 0 times the accrued liability at time 1. The accrued liability comes from the past salaries plus this year's salary times the accrual rate of 2%. Of course, the discount factor 1.05 to the negative 1. And here we have the values of that account for the present value, for the actual present value at the time of retirement with this annuity value at age 64.5, which is discounted back by half a year to age 64, and then this is the probability of the payment, R64 over L63, but one more year of discounting with this 1.05 to a negative 1, and then retirement age 65, and the probability of it discounted 1 year and then one more year here. And all of these numbers here are available from the table, so we plug them in, do the calculation, we get 566,638.40, and then the normal cost is calculated from that basic recursive equation. Everything else is known, so we treat normal cost as the unknown, and we calculate it to be 36,085.98, which is 36,000 to the nearest 1,000. For Part C, the expected present value of the health benefits is benefits accounting for retirement at age 63 and a half, accounting for the probability of retiring then, the discount factor because of the retirements happening in the middle of the year, and the annuity factor for the premium payments. So this accounts for how the premiums will be paid as an annuity and how when it starts and how it will be paid in increasing, and this is the benefit rate. And the same for age 64, with the actual retirement moment is 64.5, that's why we're using it here, and then age 65, the normal retirement age. And we have a double dot b x t equal to a double dot b x 0 for any positive t. Therefore, b64 is 3.5 is 2,000, the initial rate, times 1.035 cubed times 1.03.5. 2,000 the rate from the age 60, but we're at age 63, so that's why we multiplied by 1.035 cubed, and this 0.5 is accounted in multiplying by 1.03 to the fifth, and here is the rate. And here we have the same for age 64, which again accounts for mid-year retirement, and then 65, the normal retirement age. And here we have again the rate. So we plug those values in, and the annuity factors as well. Now do the calculation, and we get 64,555.47. Please remember this is copyrighted material. The problem itself comes from the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.